Okay, so I'm going to record projects 3 and 4 for our group, which consists of me and Mia. So for reader writer, we have reader writer part 1. So for assignment 3, we know that we're working with simulating the reader writer problem, where you have multiple readers accessing a shared resource, shared memory, and you have multiple writers trying to write to that same shared memory. The problem lies in when you have writers trying to write to a location or write to memory that readers are trying to read, which can't happen. So this entire program was to simulate that effect. So we use threads where we have, we created the threads for readers, we created the threads for writers, and we have a thread, a num thread for readers and a num thread for writers, where we know that there's for every one writer, there's 5 times the amount of readers. So we created those threads, we appended them to the list, either a reader thread list or writer thread list. We shuffled them, we start them, and then we join in the final end and log times. And then we displayed it to memory. So I'm just gonna like jump into it so I don't waste too much time. So record it. Let's go to assignment 2, assignment 3. Python in the 2. And then you pass in 1 writer for this one. So it's gonna take a while to run, but when it's actually finished, it'll just display a time. Shouldn't take more than 2 minutes on average when I ran this one, locking and unlocking based on the entire memory section. I won't run the second one because it's kind of the similar process where it does the same thing, unlocking based on the memory location. So if you're in A, you write to A, read in A. Similarly, when I run that one on average, I kind of like left a note for myself when I ran it last night. It takes about 33 minutes to finish. Should be finishing anytime soon. And then when it's actually finished, it'll write to a file called, it'll create a file called reader writer memory JSON, which prints the final memory locations or like the changes to JSON file. So this is like kind of what memory would start with, and then it'll like change it, all the locations when it's actually finished. And through the implementation, so we generated the instructions with this, generated that memory random instructions that you kind of provided. And then we created the, whether they're reader files, we just put in type reader as you kind of like helped through with this code here. Then we generated these reader files and then similarly the writer files. Okay, it should be done pretty soon. Because like I say, it's 2 minutes to actually run it. I won't run the second one, but it operates in the same like on the same like premise that it does the same thing where we're getting the lock for a reader lock or a writer lock. So if it's reading, everybody could read, obviously. And then if it's writing, then nobody could read if the person is writing in that location. So kind of like you see that, oh, this writer was writing to this location. Okay, so it's actually done now. So the rich thing is kind of like thing, but it kind of like prints everything when it's done. It's so we can see the time. Let's go all the way to the top. The time it takes 2 minutes and 30 to run to completion. And let me show you the how memory is at the end. So it should have created the reader writer 22. Yep. So this is memory changing. Memory changed quite a bit from the original memory. Okay, and this is reader writer part 1. Now let me run part 4 is we kind of did this similar thing. We use threads. We use threads. But instead of being threaded based on a reader files, readers being the process and writers being a process, separating them. It's just processes, and you just operate it with a similarly shared memory location, and you have like a priority section, and the priority has first come on all of the they have first come over to all of the process to run, and then everybody else comes in. So I'll kind of like start up the running process. Like I say, it takes quite a bit to run to completion, but I'll just start it running it, and then I'll kind of like cut it off and show you, the simulation of the last time we ran it. Last time we ran it last night, it was like 30 something minutes, and then they print memory to this memory final JSON. So let me run this one so you can see kind of like how it like operates. cd dot dot cd assignment 4 Python. Yeah, we kind of have like how the program operates, So this one simulates, it's kind of similar to the other one, but it simulates like the race conditions, as we're trying to like see if we can get a race conditions with a private memory space, like private instructions or priority instructions. So with this one, we kind of like did the same process with the threads. We show where they are, where the threads are at, like whether they're reading in a specific memory location or writing in a specific memory location. And then we have also what is being loaded in a specific register at the time too. So in this one, it's loading 1 into register 2, and this one is loading 2 into register 2. So we have 4 registers as kind of like, it's kind of like we created the instance object of the register class that was kind of given. We created 4 of those registers, and then we kind of went through the similar process for reader writer part 1, where we lock, unlock similarly, and then we show what's happening at each step. Is either they're reading or they're writing, or they're loading something into a register. So like I said, I won't run the whole thing because it's going to take quite a bit to run. I just wanted to like show you the startup process, with the design using Rich. So let me kind of like show you what memory is like after the last time I ran it last night. So it's kind of like the final results from memory. It ran to memory final.json, kind of like let it write to this. It printed to this. So this is kind of like how memory changes. And like, like I said, a lot of these goes on a lot of like decimal places, do the calculations, but yeah, this is kind of what we have. Final thoughts on the class and the projects and stuff like that. I'd say in this class, definitely learned a lot. Came into the class, kind of shaky on the Python, but I'd say like after like struggling through, I definitely say that I got better at it, or that we got better at Python in general. We understand, how the under the hood stuff, how the CPUs work, how, the reader writer problem, how the shell commands is, I kind of use it throughout the video, Class allowed us to learn a lot of material in a kind of short time through a sink or swim. Is either you learn it or you don't. So yeah, and then Mia will be recording the video on the other assignment 2, the CPU scheduling one. So yeah.
Hi, this is Mia Branganetash. I'm going to talk about our second project, CPU scheduling. So this project mimics the CPU schedulings of processes, by using scheduling algorithms such as first come, first serve, shortest job first, priority based, and round robin. So this project aims to find that which algorithms work more efficiently by comparing wait times and CPU usage. And now I'm going to run the project and show the results. So first I'm installing Rich. So there is the usage, as you can see. We need to choose which algorithm we want to use. So 1 for first come, first serve, 2 for shortest job first, 3 for priority based, and 4 for round robin. So at the beginning, I want to start with the first come, first serve. And for CPU, I'm choosing 10. For IO, I'm choosing 1. So this takes a while. Because of that, I'm just gonna stop the program and show the screenshot of the results. Okay, and in here, as you can see, this is for first come, first serve results. And shortest wait time is 293, and longest wait time is 337, and average wait time is 152, and CPU usage is 3.7%. And for shortest job first, I also use the same number of CPU and IO to comparing equally. You can see that average wait time is 190 and CPU usage is 44.6. So by comparing first come, first serve and shortest job first, and shortest job first has more average wait time and more CPU usage. And so in that case, we can say that first come, first serve is better than shortest job first. And now let's look at the priority base. Average wait time is 133 and CPU usage is 3.6. As you can see that this has less wait time and less CPU usage. And now let's look at the round robin. So in round robin, we have quantum. So we give quantum in the code manually, actually. So first quantum, we choose 4. And average wait time is 275 and CPU usage is 5.8. So actually this is the worst results that we got so far. So let's change the quantum as 7 and see the results. So average wait time is 257 and CPU usage is 505.6. So the results are better, but still has more times and CPU usage by comparing to other algorithms such as first come first serve, shortest to first. So at the end, we see that priority base has the best results, then first come first serve, then shortest of first, then round robin. So lastly, I wanna compare the same algorithm with two different numbers of IO. For that, I choose first come first serve with two different IO. So let's look at average wait time for one IO is 152. Average wait time is for two IO is 7. So as you can see that there is wait time dramatically decreased, and also CPU usage became much better, like 3.7, 3.2. So yeah, my presentation is over right now. And for conclusion, I can say that this project taught us how scheduling algorithm works and which factors affect the efficiency. So it was really helpful, and yeah, that's all. So thank you.